Okay, so picture this. You're in orbit, there's no GPS, no digital map on a screen, just you, the stars, and the incredible blue Earth spinning below. How in the world do you know where you are? Well, for over 40 years, the answer for Soviet cosmonauts wasn't a screen. It was an amazing symphony of clockwork.
So let's just ask the question straight up. You're hurtling through space at 17,000 miles per hour. That's a trip around the entire planet every 90 minutes. You absolutely need to know your position, not just for fun, for talking to ground control, for running experiments, and maybe most importantly, for making it home in one piece. So, how'd they do it? The answer is, you used this, the Globus INK. Now, yeah, it kind of looks like a desktop globe you'd have in a library, right? But don't let that fool you. This thing is one of the most brilliant and long-lasting pieces of space hardware ever made. It's an electromechanical analog computer, basically a clockwork brain that guided nearly every single Soviet and Russian crewed mission from the very beginning all the way up until 2002.
All right, let's get into it. To really understand the Globus, you've got to wrap your head around a totally different way of thinking about technology. This isn't some clunky, primitive machine. No way. This is a highly advanced mechanical computer.
And this is where you see this huge split in philosophy during the space race. The US, well, they dabbled with mechanical stuff on the early Mercury flights, but they went all in on digital computers super fast. By 1961, they were already developing things like the Gemini guidance computer. The Soviets, they took a different path. They were all about reliability, stuff that was tough, that could handle radiation, that you just knew worked. They stuck with and perfected this analog tech for decades. It was a reliability you could literally see and touch.
And what did that philosophy get them? More than 40 years of service. I mean, think about that. This thing, or its family of instruments, was there from the very beginning with Yuri Gagarin himself in 1961, and it kept flying on the Soyuz until 2002. That's just staggering. For any piece of hardware that's keeping astronauts safe, that is an unbelievable run.
Okay, so you're probably wondering, how did this thing actually work? Here's the key thing to get. The Globus had no idea where it was. Not really. It wasn't getting signals from GPS, because, GPS didn't exist yet. It wasn't getting constant updates from the ground. It used a technique that's as old as sailing, called dead reckoning.
So what is dead reckoning? Well, in simple terms, it's like navigating in your car if all you had was a compass, a clock, and your speedometer. You know where you started, you know how fast you're going and for how long. From all that, you calculate where you must be now. The Globus is just an incredibly sophisticated space-age version of that same idea.
Here's how it worked in practice, broken down into 3 simple steps. First, you got to tell it where to start. The cosmonaut would get the starting coordinates from ground control and literally turn these knobs to set the globe to that exact spot. Second, you hit go, and the machine kicks into gear using a super precise 1 pulse per second timer to mechanically crunch the numbers on how far it's traveled. And third, it just updates. The globe physically rotates under this little fixed crosshair, showing the spacecraft's new position in real time. Simple and absolutely brilliant. But, and this is a big but, there's a catch with any dead reckoning system. It's called cumulative error, or drift. Think about it. Any tiny little error, a slight miscalculation of your speed, a tiny bit of atmospheric drag you didn't account for, it all starts to add up. Over 1 orbit, it's small. Over 10 orbits, now you could be way off. That's why the cosmonauts had to do a periodic correctia, or correction. They'd get fresh data from the ground and manually reset the Globus to get it back on track. Okay, so we get the basic idea, but how does a box of gears actually do math, right? We've talked about what it does, now let's pop the hood and see how it does it. We're going to look at the guts of this clockwork brain. Forget everything you know about CPUs. No silicon, no transistors here. The brain of the Globus is pure mechanics. We're talking a beautiful, complex dance of gears, these specially shaped metal plates called cams, and some really clever little gadgets called differentials. These aren't just spinning parts, they're actually performing calculations. The math is happening in the motion itself.
So the real workhorse inside this thing is the differential gear. Think of it as a mechanical calculator for adding and subtracting. It's pure genius. You have 2 gears spinning into it, and a third one comes out spinning at the sum or the difference of their speeds. The Globus has 10 of these, and they're what let it do things like add a tiny speed correction to the main orbital speed. Okay, but how does it handle those little speed adjustments? See, the whole system gets its tick from a part that clicks forward at a steady 1 pulse per second. But orbits aren't perfectly steady. Your speed changes a tiny bit with your altitude. So how do you turn a fixed, steady click into a variable speed? The solution? Oh, it's a work of art.
It's this thing, the spiral coned cam. The best way to think of it is like a continuously variable transmission, or CVT, in a car. You've got this cone spinning and a little follower that rides along its surface. If the follower is at the skinny end of the cone, the output is slow. If the cosmonaut turns a knob and moves the follower to the fat end, the output is fast. It's that simple, and it allows for incredibly precise adjustments. We're talking down to 1/100th of a minute for the orbital period. Just amazing. Okay, so speed is one thing, but an orbit isn't just a straight line. It's a complex curve over a spinning planet. Think about the latitude. It's not changing at a constant rate, right? It's going up and down in this perfect sine wave. So how on earth does a mechanical box calculate something like a sine wave?
The answer is with another type of cam. These precision cams are basically math made physical. They're just chunks of metal that have been machined into the exact shape of a mathematical function. So as a gear turns at a steady rate, a follower rides along this custom-shaped edge, and its movement perfectly mimics the sine wave needed to drive the latitude dial. It's like a physical lookup table. It's literally solving trigonometry with a piece of metal.
Okay, so we've looked at all the key pieces, right? The clock, the adders and subtractors, the variable speed gearbox, and the function generators. Let's put it all together now and see how the information flows through this whole incredible machine. This is a great way to see it all in action. So it all starts with that 1 pulse per second click. That's our base clock speed. Then the manual dials set the position on that spiral cone cam, which adjusts that base speed to the exact orbital period needed. Next, all those inputs go into the differential gears, which add everything up to create one final precise rotational speed. And that final rotation is what turns the globe and drives those other cams that calculate the latitude. From a simple click to a full 3D position. But wait, there's more. The Globus actually had 2 key modes. The first one is what we've been talking about, the standard mode that just tracks where you are right now. But the later INK model had a second and absolutely critical mode for landing. The cosmonaut could flip a switch, and a whole separate motor would kick in and fast-forward the globe. What did that do? It showed them exactly where they would land if they fired their retro rockets at that exact second. I mean, talk about a crucial piece of information for getting home safely.
You know, when you step back, the Globus is so much more than just a clever piece of tech. It was a true cornerstone of the Soviet space program for decades, and it's left behind this just incredible legacy.
I mean, just look at its history. The first version flew with Gagarin in 1961. The more advanced INK model came along in '67 for the Soyuz spacecraft. They even made a special one for the Apollo-Soyuz mission in '75, which is amazing. It actually had NASA tracking sites printed on the globe. And it flew right up until 2002 before it was finally replaced. That's just wild.
And I think this quote from researcher Ken Sheriff just nails it. Back in the 60s, a digital computer couldn't give you a high-res, full-color display. It just wasn't possible. But the Globus, it gave you this beautiful, intuitive 3D map of exactly where you were over the Earth. It wasn't primitive. It was actually a better display for its time than anything digital could offer.
And really, that's the big takeaway here. The Globus INK is proof that there was another way, a different path for technology. It's a powerful reminder that sometimes the most elegant and reliable solutions aren't made of code and circuits, but of gears and levers. So it kind of makes you wonder, right? In our world today, where we depend so completely on digital everything, what can we still learn from the incredible, tangible ingenuity of a Clockwork brain?